Il prossimo talk sarà dato dalla dottoressa Sofiya Milman, che è Professor of Medicine and Genetics e Interim Vice Chair for Research, Department of Medicine, Director, Human Longevity Studies, Institute for Aging Research, Albert Einstein College of Medicine a New York. E prego.
It is a pleasure to be here this afternoon. Thank you very much to all the organizers, Viviana, and everyone else for allowing me to be here. So today I will tell you about growth hormone and its role in aging. I think many of us have seen this slide before in different forms. And what it tells us is that age itself, or aging, is a major risk factor for all age-related diseases. So on the x-axis, we see age, and on the y-axis is the logarithmic incidence, right, or the risk for all of these diseases. And we can see that for heart disease, for dementia, for cancer, for diabetes, the risk for all of these increases logarithmically as we age. And so the way things are now can be represented by these bars. At the top bar, the length of the entire bar represents our lifespan, right, or the number of years that we're alive. And the orange portion represents the part of our lives that we spend with disease or chronic conditions or disability. And if the average lifespan is about 85 now, then 20 to 25 years, unfortunately, I spent dealing with chronic conditions, diseases, and disabilities. And what we're all hoping to achieve is not necessarily having everyone live to 120, but to live to 85 healthy years, right? To really compress and reduce the amount of time that we're dealing with chronic conditions. And that's represented by the second bar, right? Where we're reducing the orange portion of the bar. We're reducing our time spent dealing with disease. Now, if in the process we do extend our lifespan, right, and if we're able to make everyone live to 120, I think most of us will take it if, right, we don't extend the period of disease. We don't want to live for 60 years with disease. But if we extend our lifespan, but are still able to keep the period of disease compressed, right, very short, only at the very end of life, or maybe not at all, then that's what I think most of us would want, right? So we can continue to have a good quality of life as we age. And many will ask, is this a realistic expectation, right? Is this science fiction? And I will tell you, no, it's a reality, because there are people among us, right, who are centenarians who live to age 100, but they're not only living long, they're also living healthy. And what I'm showing you here are disease-free survival curves, which means how long did people live without developing any age-related diseases. And the last line, the blue T line, right there, are people who live to age 110 or older, okay? And the black line are people with average lives. And what we're seeing here is that 90% of people who lived to age 110 did not get any diseases until they were 90. So that tells us that it is absolutely plausible, and our bodies are capable, biologically capable, of living long and healthy lives. So the question is, how do we get there? And so what we study in a lot of other groups around the world and here in Italy, we're very much interested in studying these unique individuals who are age 100 or older who are healthy in order to understand how did they get there, right? What is it about them that allows them to live not only long but healthy lives? And sometimes people look at factors that change as we age, right? To see, well, if something is high when you're young but low when you're old, or maybe the opposite, maybe that's a driver of aging. And one such hormone is the growth hormone. and the name, as it implies, is that the hormone is responsible for growth. That's what allows us to grow taller when we're kids, and our organs to grow and develop. And when we do research in people, it's very difficult to actually measure growth hormone itself. So we measure a surrogate, like a marker of growth hormone called insulin-like growth factor 1, IGF-1, which is produced in response to growth hormone. So they go hand in hand. When one goes up, the other one goes up. When one goes down, the other one goes down. So we can rely on IGF-1 as a marker of growth hormone levels, and throughout my presentation, I'll use them interchangeably. So here's what happens to our growth hormone levels throughout our lifespan. They're relatively low when we're first born, but then as we get older, the levels rise, and the peak actually occurs in the second decade. That's when we're growing, right? That's our teenage years. That's when we're getting taller. But then the levels decline very quickly, and they continue to decline as we age. And when people have looked at this pattern, they said, well, maybe because the levels decline, that's why we're aging, that's why we're getting disease, and we're getting disabilities. What happens if we actually bring the levels back up to youthful levels, right? Maybe that will be our fountain of youth. And they've tried it. So in 1990, there was a study done in the United States in men aged 60 and older who were given growth hormone for about 6 months. And here's what happened. So they noticed that they increased their lean body mass. They reduced their adipose, fat tissue. The lumbar spine bone mineral density, right, the strength of the spine bone improved, and their skin thickness improved. Looks like they found the fountain of youth, right? Looks great. But they also found that their blood pressure went up, and their blood sugar went up, and many of them developed diabetes. And so something that looked like it might work has actually increased the risk of age-related diseases in people who are already at risk. And so maybe this wasn't such a good idea after all. And when we actually look in nature, right, so a lot of us have spoken about using other organisms in identifying drivers of aging. When we look across nature, we find that animals or other model organisms that have low growth hormone levels actually live longer. And that's true for worms, flies, mice, and actually in some people who are centenarians, we have also found genetic changes that reduce the function of their growth hormone, suggesting that this is a conserved mechanism across all species that allows people to live longer. And so we have decided to look in our cohort of centenarians. What are their levels and what does it predict? So here we're looking at survival in people who are age 90 and older, and this is a woman only. And the green line represents those who have low growth hormone levels, and the orange are those with high. The x-axis is how long they live after we measured their level, and the y-axis is how many of them are still living. And what we find is that after 3 years of follow-up, those who had low levels of growth hormone actually were twice as likely to still be alive. We didn't see that in men, but we had a very small number. Now, this is growth hormone, so it doesn't only allow us to grow taller, it also allows tissues to grow and cells to grow. So if someone has cancer, right, growth hormone can actually promote the cancer growth as well. So we looked at people who had a history or did not have a history of cancer. So in those who never had cancer in their life, it didn't seem to matter what your growth hormone level was. But in people who did have a history of cancer, either past or present, those with lower levels of growth hormone actually survived longer than those with high levels. And so 50% of people lived twice as long who had low levels, and the number of survivors were 3 times greater at 3 years of follow-up than those with low levels. Okay, but that's lifespan, right? We talked about, well, okay, maybe we want to live long, but what we really want to do is live healthy. So does it allow people to live healthier? And so we looked at cognitive function or memory in these individuals as well, and found that in women who had lower levels of growth hormone, so they were in the lower 33% for their age group, for their population, they were half as likely to have dementia and memory problems, right? So they were not only living longer, but they were living healthier. They were maintaining their cognition. We didn't see that in men. Again, we might have been underpowered. Okay, so that was 90 and plus, right? But you have to get to 90. How do you get to 90? So we looked at people who were middle-aged, 65 and older, and found the exact same thing. So here the orange line represents those with high growth hormone, and the blue lines are those with low growth hormone. And what we found across the board for everyone, men and women independently, was that lower levels were associated with better cognition. That's the top line. They had less multimorbidity, so this is looking at any age-related disease like cancer, cognition problems, diabetes, heart disease. So those with low levels were less likely to develop all of those. And they had less mortality, right? If they had lower levels of growth hormone, they were less likely to die. And when we looked at other studies, we have found a very interesting conundrum. So those that only looked at older people found that growth hormone was harmful for them. And those are the studies here on the bottom, right? It increased their risk. Anything above 1, that means your risk is more than, average. But when we looked at young people, we didn't find that relationship. So we're a little bit puzzled, right? Why are we seeing it in old and young? What's going on here? So we did a very large study in over 400,000 people that ranged in age from their 30s to their 70s to try and figure out this puzzle. And this is a cohort from the UK Biobank, so from the United Kingdom. And I will walk through this figure to explain to you what we found. So when we look on the left side of the curve, right, these are people with low growth hormone levels. And we have two curves. We have a curve for the young, that's the green, and a curve for the older people, that's in red. So those who are young and have low levels of growth hormone have a much higher risk for disease and dying. But those who are older are not at as great of a risk, right? Their risk is significantly reduced compared to the young people. On the other hand, when we look at the high levels of growth hormone, the people who are most at risk are those who are older. Younger are also slightly at risk, but not as much as the older people. And in fact, the lowest risk is here, so somewhere between the 25th and 50th, maybe 75th percentile, right? So we found this dichotomy where something that's good for younger people is actually harmful for older people. And that brings us to the concept of antagonistic pleiotropy. So in nature, we often find things which may be good for the young, but bad for the old, or vice versa. And it is really important for us to recognize that, and not necessarily to try to make older people young in the same way that you would just replace something that they're missing. And this is really our hypothesis and how we're going about this to explain why that may be. So in youth, right, you need growth hormone for development, growth, injury repair, because it promotes cell growth, cell proliferation, cell survival. But when we get older, we don't need to grow anymore, right? We've reached our maximum height. If we're going to promote growth, we might promote the growth of cancer cells. And when we're actually older, what we want to do is we want to maintain our bodies, right? We want to repair and maintenance. So we want to move our energy away from growth and towards maintenance and repair. But if we maintain high levels of growth hormone, we will not be able to maintain our bodies because growth hormone promotes reactive oxygen species generation. It inhibits stress resistance that our bodies naturally possess, and it also inhibits a process called autophagy. And those of you who may have been in the conference for the past few days have heard about that. That's a process where the cell self-eats, right? It eats the debris, the toxic proteins that accumulate in the cell and don't allow it to function well. So we want to maintain those processes. We want to eliminate those harmful proteins. So we want to shift energy away from growth and towards repair. Because in aging, we have diminished resilience and accumulation of cellular debris. So here I'm going to show you this complex figure, but what its goal is really to show you, these are the pathway of growth hormone, right? This is how it works. But that's not really why I'm showing it to you. I'm showing you that we have medications already used for other diseases that can block the growth hormone pathway at different areas. Some of these are already used for a disease where people make too much growth hormone, called acromegaly. Others are used for other conditions. And of course, if we were going to try to use a medication to block growth hormone, we would never want to use it in young people, right? Because they're still growing and developing. So we want to use this drug when somebody is older, later in life. But is it going to work, right? Is it still going to work in older individuals? So a colleague of mine actually did a study to answer that precise question. He administered a growth hormone blocker to mice that were middle-aged. So they were 80 weeks of age when he started. And what he found was that even if you start this treatment in middle age, it still extended the lifespan of these mice. So the red line are the mice that got the treatment, and you can see that 50% of them were living longer. And so that really allows us to kind of go to the next step and say, okay, we can potentially use this treatment. It's relatively safe because it's already being given to many people for other conditions, and we can start it in middle age, and it will probably still have benefit. And now we're starting a preclinical trial in mice for now to test a compound that blocks this pathway to see if it'll prevent Alzheimer's disease in mice. So just to summarize what I showed you, aging is under biological control. Growth hormone signaling is a conserved pathway of aging. Reduced growth hormone signaling may protect older adults from age-related diseases. And we need to identify biological pathways that regulate aging, which can then lead to the development of therapeutics that delay aging and age-related diseases.